Good afternoon, everyone, and welcome to our new live event under the Cold Chain Innovation Hub in Philippines. We are very happy to host another technical training workshop, this time focusing on advanced technologies for industrial refrigeration. This is a continuation of our series that was focusing on commercial refrigeration, as well as the market research conducted on the ground, solar cooling technologies, and other items of the food cold chain technologies that we are covering. We have prepared a very good program. Over the next 3 hours, you will hear from several experts. I'm here together with our colleagues, Gilda, who is a project leader of the cold chain project in Philippines, as well as my colleague, Devin. So I will be guiding you and moderating the discussion together with my colleagues over the next 3 hours. Looking forward to sharing a lot of exciting content with you all. First of all, a few words on our agenda. We will have a short welcome from Gilda, who will be introducing the project backgrounds and the updates. And then we will dive into a rather technical and rather specialized content, starting with Stefan Jensen from Scantech, talking about energy efficiency benchmarking and low charge direct expansion ammonia systems. We will also hear from the local expert, Cesar Luis Lim from Philippines, who is having a very rich experience with ammonia in Philippines. After a short coffee break, we'll be following with two companies taking the topic of industrial refrigeration and the advanced technologies in their presentation. One of them, GEA, will be focusing mostly on ammonia technologies, but as well as CO2, focusing on all the aspects, installation, maintenance, and other topics under the subject. And finally, we will hear from Carrier that will be focusing on CO2 transcritical as a solution for industrial refrigeration technologies. So a very packed program, and without further ado, I would like to take you through some of the aspects of the platform that we are using. So all of the delegates, yourself, can now have the same, you can see this window. This is what's in front of you right now. So please note that the partners of the project are on the left. You can click and access their websites to learn more. You can also sign up for our project newsletter. And you can, of course, access the website. On the right side, you will be seeing all the presenters in their webcams. Below them, you can scroll down and see the profiles of our speakers, and also contact them via LinkedIn or email, as well as in the very bottom right side, you will find a number of resources for the project. Among them are our YouTube channel with all the previous events that were recorded and edited, as well as you will find a Zoom link. The Zoom link will be very useful at the end of our event when we will gather informally. Everyone is welcome to join us for a half-an-hour informal discussion post event on 24. So we will again repeat this message throughout the event. All the windows are, you can edit them, you can make them larger, smaller, you can move them around your screen as you please. Stakeholders present today. I'm very pleased to share with you that we have more than 200 people sign up for the event, and they represent various stakeholders, very important for cold chain industry, as well as we have a wide range of countries represented among our delegates. So we're very pleased to be hosting all of you today. And with a short notice, another event that Cold Chain Innovation Hub will be participating is the virtual trade show that will be taking place next week on Tuesday and Wednesday. And Cold Chain Innovation Hub will have a 1-hour live webinar with all the project partners speaking and giving updates. So do not miss the global virtual trade show next week. You can sign up for free. With that, I would like to give the word to my colleague, Gilda, who is joining from Philippines, and she will help to introduce the project to some of you who may be joining us for the first time today. So Gilda, hello, can you hear us?
Yes, hello, good afternoon, Ian. Am I clear to you?
Very good. We can see you and hear you very well. So please take over the virtual stage.
Okay, then. Good afternoon. I'm so glad to be here with you this afternoon, and I'm going to present what our project is all about. By the way, I'm Hilda, and I'm the project leader. So let's start. The United Nations Industrial Development Organization, or UNIDO, is implementing a project in the Philippines called Global Partnership for Improving the Food Cold Chain in the Philippines. It is funded by the Global Environment Facility, or GEF, amounting to $2 million plus co-financing by other institutions amounting to around $25 million. The Department of Environment and Natural Resources, DENR, is our government partner, while other executing partners are SHECO, Technical Education and Skills Development Authority, or TESDA, and financial institution. The goal of our project is to identify, develop, and stimulate the development of low-carbon, energy-efficient refrigeration innovation technologies and business practices in the Philippines for use throughout the food cold chain whilst increasing food safety and security. Through the project, it is aiming to establish a global partnership between the public sector, the private sector, and financial institutions for promoting of investment and support of best available energy-efficient design, technologies, and practices transfer. The project will concentrate on the comprehensive transformation of the commercial, industrial, and transport refrigeration system, designed to address the following. Number one is the impact of refrigeration to the global warming through the emission of refrigerants and through energy consumption resulting to greenhouse gas emission. And then number two, food losses due to inadequate cold chain equipment, which is affecting both the farmers and consumer. We need adequate, fresh, and safe food are critical to our country that is home to 100 million Filipinos. The project will achieve such objectives through the implementation of 4 substantive components and associated outputs. Component 1 is the policy and regulatory assessment on the use of low-carbon and energy-efficient technology within the food cold chain. This is under the responsibility of the DENR. And then, Component 2, awareness and capacity building in the use of energy-efficient, climate-friendly, and safe alternative in the food cold chain under SHECO and TESDA through the Cold Chain Innovation Hub. And then, Component 3, technology transfer and establish partnership among key stakeholders also under SHECO and TESDA through the Cold Chain Innovation Hub. And lastly, the monitoring and evaluation will be done by UNIDO. What is this Cold Chain Innovation Hub? The Cold Chain Innovation Hub is the official platform of the project. It will serve as the project's central ecosystem of technical resources, training, knowledge sharing, and stakeholders collaboration. It is expected that through the CCI-Hub, new technologies made available in the country, partnership between key stakeholders established, and financing scheme to develop bankable investment project put into practice. TESDA was selected as the national entity to host the CCI-Hub at its central office located in Taguig, Metro Manila. However, because of our present situation, the CCI-Hub is concentrating on its virtual platform, but very soon this year, the physical hub will be established. Let me share to you what we have done so far. So we have these learning modules, we have the report, we have various videos, we conducted several webinars and technical training workshops. We participated in international events such as the Natural Refrigerants Virtual Trade Show last year, and we will again, as mentioned by Jan, we will be again participating this year, this coming March 30 and 31. So please subscribe to CCI-Hub website for knowledge materials and updates on events. So, guys, thank you very much for listening. I hope you have a good background what our project is all about. Now, back to Jan.
Thank you very much, Gilda. Very good to have this overview. I will just share one more update. During the live webinar next week under the Global Virtual Trade Show, we will be presenting a sketch or futuristic vision of the physical space that has been identified by our project partner TESDA. So we'll be sharing our vision for the physical hub that will be built hopefully as soon as this summer. So we welcome you again to join our upcoming event next week. With that, I would like to invite our next presenter, our first technical presenter, Mr. Stefan Jensen, who is the Managing Director of the Scantech Refrigeration Technologies. He is a known expert in the field of industrial refrigeration with focus on low-charge direct expansion ammonia. So Stefan, please join us if you can hear us. Hopefully we'll see you in the camera very soon. We have known Stefan for many years. He is regularly attending academic conferences around the world and presenting at different conferences about the topic, about the energy consumption and best practices. So we are very happy to have Stefan today as a true expert. Stefan, I can see you joining today. We have just introduced you briefly. So this is the time is ready. We are ready for you. Please join us, and you can start your presentation.
Thanks for your introduction, Jan, and good afternoon, everyone. I will talk to you about two main things. First of all, a little bit about technology. This is how these centralized low-charge ammonia refrigeration systems are designed and put together. And the second part of the presentation will be about mainly about the business aspect of things. What are the advantages? How low can the energy consumption go? And how about return on investment when investing in a centralized low-charge ammonia system? So we have quite a few slides. So some of the slides I'll just go through rather quickly, simply because otherwise I think we're going to run out of time. Here we see some of the bullet points of centralized low-charge ammonia systems. Just to as an introduction, the main features are significantly lower energy consumption, significantly lower ammonia inventory, somewhere between 3 and 5 times lower than conventional liquid overfeed ammonia systems. There are no ammonia pumps, no ammonia overfeed pumps or ammonia circulation pumps. We don't use superheat control. We control the injection into the evaporators by means of a quality sensor. More about that a little bit later on. And very importantly, all of the suction lines and all of the risers in the system are more or less free of heavy liquid refrigerants or liquefied refrigerants. We're running overfeed or vapor content, liquid content in the vapor line coming back to the engine room between 1 and 5% coming out of the evaporator. So by the time it gets back to the engine room, those liquid droplets have disappeared. So the suction lines and the risers are more or less free of liquid. This is quite important. Now, first of all, let's have a look at a typical installation. This one was completed in 2013 in Perth. There are about 23 or 24 installations operating in Australia now, and one is in China. What we see here is a 40,000 cubic metre refrigerated warehouse for a food service company. Building exterior is up in the top left-hand corner. The plan view is to the right. You can see there's a freezer and a chiller, what is called a flower room and an entry room. And the plant room is that little pink rectangle down in the bottom right-hand corner. This is a plant that was using superheat controlled injection and evaporators with internal surface enhancement. 25 kilowatt hours per cubic meter per year is the specific energy consumption of this installation. It is still operating. There has been no real technical issues. Here you see a picture of the valve station used for the freezers. It's no real surprises here. You can see it is all quite conventional. The main differences are these. There is an oil drain from the distributor, the liquid distributor, the inlet evaporator. There's two hot gas solenoid valves, one for the condensate tray and one for the coil. The reason for that is to be able to warm up the condensate tray before hot gas is injected into the evaporator coil. These evaporators defrost rather quickly, and if the condensate tray is not warm by the time the condensate starts to hit the tray, there's a risk that it might refreeze. I haven't shown you the way the condensate is returned, but it is returned via a high pressure float valve directly back to the intercooler, not the low temperature accumulator, but the intercooler. Here we see a couple of images of how the liquid is distributed in the evaporator. This is done in these types of plants predominantly with what we call gravity distributors. Kuba in Germany had a patent on gravity distributors about 40 years ago or more. It has long since expired. What you see on the left there is another type of gravity distributor that comes from the US. Some people call it a tank distributor. And on the left-hand side, you see a coil being pressure tested. It is fitted with another type of gravity distributor. It basically looks like a bucket with a distributor lead coming out of the bottom. The advantage of a gravity distributor is that they will ensure uniform distribution over a very wide operating range from about 0 to 700%, whereas conventional distributors have a much narrower operating range, somewhere between 50 and 140% or so. Outside those operating ranges, or that operating range, liquid distribution, certainly at the lower end, has a tendency to become non-uniform. And at the upper end, there's simply not enough liquid going through to satisfy the evaporator requirement. May I mention before that we do not control the refrigerant injection into the evaporator by means of superheat control. We use some sensors that are able to measure the X value or the quality value of the vapor leaving the evaporator, and convert the quality signal to a signal that we can feed into the centralized control system, the 4 to 20 milliamp signal. Let's not get into too much detail about how this sensor works. This is frankly a matter for the manufacturer. These things come from Denmark from a company called HB Products. What you see there on the shot on the on the right, is one way of installing the sensor. There are other ways. Some of the later plants, we have removed the sensor from the refrigerated space and up into the ceiling space, where it's much easier to service, and it doesn't jeopardize the ability to control the refrigerant injection into the evaporator. It's very important that the sensor is not submerged into liquid. If it gets submerged into liquid, it has a tendency to send a signal that the control system can't read. In those situations, we switch to superheat control until the quality sensor has found its way again, and then we switch back to quality control of the injection. So this screenshot here is from a SCADA system of a plant that was installed approximately 5 years ago. And what is important and interesting here is when we compare the superheat signal with the quality signal leaving the evaporator. The superheat signal you can see down the bottom there, the green signal, and the quality signal is the top signal called X out. You can see we can have wet suction at the same time as we have positive superheat. This is a peculiarity we observe in almost all the systems that have been installed. You can also see that the room temperature is quite steady, and you can also see that the expansion valve position, this is the one that is titled TXV, more or less there in the middle of the picture to the left. The TXV position, or the expansion valve position, does respond to wet suction. So when X out indicates wet suction, the expansion valve closes. If this expansion valve was to control in response to the superheat signal, it is highly likely that the operation would be far more erratic and hunt far more. So the lesson or the takeaway out of this is that using quality control will deliver a more stable control than superheat-based control. This slide shows a little bit more than oil management. You can also see a couple of slides there, one down the bottom where the guy is bending over a bit. That shows a dehumidifier, which is used to reduce the impact of infiltration into the cold store. The same in the top right-hand picture. There you see a horizontal air curtain, which is used for the same purpose, in other words, to minimize the amount of infiltration that goes into the cold store. This is a very, very high usage cold store. There's a very large door that is open to an area that is held at about 5 degrees C, and that large opening is used for picking of product for approximately 15 to 20 minutes per hour. It's very important to minimize infiltration here. The tank or the receiver that you see towards the left in the picture is a so-called high-pressure liquid-based oil separation system. Inside that receiver, there is a quiet area where the oil can settle down to the bottom of the tank. And once the refrigerant has been cleaned of oil, it spills over into another tank that is at the very end, the end pointing away from the picture. And from there, liquid is fed to the refrigeration system. The oil content, sorry, I'm going to turn my phone off. The oil content in the refrigerant that is fed into the refrigeration plant is less than 1 part per million. It is not necessary to use this arrangement on all dry expansion ammonia plants. If one uses a compressor that has low or compressor type that has low oil carryover, it's not necessary to do this. The cost can be reduced by not doing it. What you see in the middle of the picture, this little control column, or what looks like a control column, is actually measuring the oil reservoir in the bottom of what looks like a receiver, the oil separation vessel. And when the oil reaches a certain level in the bottom of the receiver, it is automatically fed back to the compressor sump. So this is also an automatic oil return system, which eliminates oil drainage from the ammonia system as such. Now this is quite an important graph. We can get into more detail later. You can see the graph is quite busy. What we have here on the vertical axis is the specific energy consumption in kilowatt hours per cubic meter refrigerated volume per year. And along the horizontal axis, we have the refrigerated volume of the warehouse. What is interesting here is are the green dots. These represent centralized low-charge ammonia refrigeration systems. And you can see that they're not only much lower than the other print dots in the picture, they are also forming a much tighter cluster. around that curve, which is sort of, which you might call best practice. The blue dots, they come from an ASHRAE publication, Anno 2018, Guide for Sustainable Refrigerated Facilities and Refrigeration Systems. They come from Dr. Reindl, Douglas Reindl from University of Wisconsin, and Todd Jekyll. They investigated 10 industrial refrigeration plants with liquid overfeed in the States. And the energy performance of those plants is represented by the blue dots in the picture. There are a couple of a bad ammonia refrigeration plant. The red dot in the top of the picture is a centralized flooded ammonia refrigeration system with economized single-stage screw compressors. So it's not very surprising that that plant performs quite badly. And later on, I'll show you some transcritical CO2 systems, which are not as bad as the red dot here in the picture, but they are much worse than the centralized low-charge ammonia systems. This is an image from a plant in South Australia that was installed about 5 years ago. You can read the data there yourself. This plant has an inventory that's approximately 4 or 5 times lower than the equivalent liquid overfeed system. It uses reciprocating compressors, and it uses glycol, reticulated glycol, for the medium temperature service. This is one of the reasons that the inventory in this plant is relatively low at 200 kilos. Again, this is a refrigerated warehouse that is approximately 40,000 cubic meters in volume, and again, it's a food service business. What you can see in the background behind the compressors is the vessel unit, and on the right-hand side in the picture, you can see a more detailed picture of the vessel unit with the plate heat exchanger. That's the blue thing there, below the intercooler and the low temperature separator. And the frosted up thing in the foreground is the oil drain vessel that separates, or that takes the oil out of the two vessels you can see above. So what I've shown you so far, and what is new here, is a reduction in ammonia inventory by about 4 or 5 times compared with liquid overfeed systems. What I haven't explained to you is the very much lower inventory in the evaporators. We are looking at somewhere between 30 and 50 times lower than conventional liquid overfeed evaporators for freeze applications. Because the density of the ammonia is higher at medium temperature, the reduction in inventory for chiller evaporators is not quite that dramatic, somewhere around 20 times lower than conventional liquid overfeed evaporators. Now, if we have a typical freezer with, say, 3 evaporators, and we lose the operating charge of one of those 3 evaporators, it is highly unlikely that the ammonia concentration will exceed 100 parts per million if the mixture is fully mixed. Now, this is on the proviso that the supply of ammonia to the evaporator is terminated immediately upon detection of the leak, and it is also assuming that the air refrigerant mixture in the warehouse is completely mixed. Now, the ideal H value of ammonia is about 300 parts per million. There are some moves to raise that to 500 parts per million. So we will be significantly lower than the ideal H value if we have a low temperature ammonia system, and if we should be unlucky enough to experience a leak. Ideal H stands for immediate danger to life and health. The specific energy consumption values, there'll be more to say about that later, are typically half of conventional plants. In some cases, it's not quite that dramatic. Sometimes it's only 1.4 times lower, And there are instances where it is 10 times lower if the liquid overfeed plant is very poorly designed or operates extensively in part load or both. I think I mentioned that we are operating at exit values or X values at the exit of the evaporator of approximately 0.95 to 0.99. This equates to 5 to 1% liquid in the vapor leaving the evaporator. So it's just, I don't think I've explained all that much about the evaporator tubes and how important it is to pick the correct evaporator tubes. There are a couple of manufacturers in the world who are able to deliver stainless steel aluminium evaporators with internal enhancement in the tubes themselves. It is possible to make the plant work with smooth tubes without internal surface enhancement, but I would recommend against using material with a relatively poor thermal conductivity. It is possible to make it work with galvanized steel evaporators and smooth internal surfaces, and it is very possible to make the the evaporator work with smooth aluminium tubes. Aluminium has a thermal conductivity that is approximately 10 times higher than stainless steel, and that is an important factor. This was established in 2008 by a gentleman by the name Dermot Cotter, who now works for Star Refrigeration in Glasgow. He did his PhD and was able to record the behaviour of boiling ammonia as a function of the thermal conductivity of the core tube material. We discussed the tank distributors. Interconnecting pipelines within the plant. These days, it is customary to use 304 stainless steel tubes for the interconnecting pipelines within the plant, so those pipes that interconnect compressors, vessels, condensers, etc. These have an absolute roughness, which is measured in meters, that is somewhere between 20 and 40 times lower than it is for carbon steel tubes. So this gives rise to a significantly lower pressure drop. Now that significantly lower pressure drop does not translate into a great improvement in energy efficiency, probably somewhere between 2 and 4%. But the energy efficiency improvement in these types of plant is not one big thing. It's a matter of combining a lot of little things to a big achievement at the end. Minimization of infiltration, we've discussed that. These plants have variable frequency drives on more or less everything except the spray pump on the evaporative condenser, which is not speed controlled for obvious reasons. Mainly we use reciprocating compressors. On some very large installations, we use screw compressors for the low temperature side, in other words, for booster operation. Currently, a 250,000 cubic metre cold store is being constructed here in Australia, in Melbourne, and that system uses two quite large booster screw compressors. And finally, it is possible to operate with minus 21 degrees C freezer temperature and minus 25 degrees C saturated suction temperature at the compressors. This leads to very, very good energy efficiency because of the low temperature difference between compressor saturated suction and room temperature. And I'll just conclude this part of the presentation with a couple of installation images. Importantly, here in the top right-hand corner, you see how a quality sensor is fitted into a suction pipe. The other ones are compressor images. You really cannot see the difference between these compressor images and those compressor images you find in conventional liquid overfeed plant. Now, I won't say too much about this other than we are able to now procure dry expansion shell and tube heat exchangers. They are very handy and very convenient for installation in sealing spaces, and they can then provide chilled glycol for process rooms immediately underneath the sealing space where the shell and tube heat exchangers is installed. On the bottom left-hand image, you see a dry expansion plate heat exchanger. We have installed one such plate heat exchanger with mixed results, but there's no time to get into that in detail. It works, but under operating conditions that I personally found surprising, and under operating conditions it doesn't work quite as well. Just a couple of pictures here of a dry expansion plate freezer. A patent is in existence in Australia and New Zealand. We are not the holders of the patent. Someone from the US is the patent holder. The other image you see to the left is the so-called low gas defrost system. This is a patent that we hold. It basically uses the heat from the subfloor heating system to defrost the freezer evaporators. So this eliminates any liquid hammer associated with hot gas defrost. Now, I don't have time to get into more detail than that, so we'll just move on. I think we'll just skip this and get into the next section, otherwise we're just going to run out of time. Now, this is the business part, if you like, of the presentation. Now, for those of you who didn't quite follow what I was saying before about specific energy consumption, I'll just explain here what that means. So, if you imagine you're a cold store operator and you know what the annual energy consumption of the cold store is, either from the utility or from the SCADA system, you take that annual energy consumption of the ammonia plant measured in kilowatt hours, and you divide that by the refrigerated volume in cubic meters. That way you get the specific energy consumption in kilowatt hours per cubic meter per year. This is a very widely used metric for comparing the energy efficiency of refrigerated warehouses without blast freezing. So what I'll be showing you in the following is for mixed warehouses. This means a warehouse comprising freezers and chillers, not chillers only and not freezers only, but a mixture of the two. And I won't be getting into too much theory. The focus will be on practical installations and recorded values of recorded SEC values. Now here we see an expanded version of the picture I showed you before. I'll just explain to you once again. The vertical axis are the SEC values. I'm sure you cannot see the numbers clearly, but up here at the top we have 140 kilowatt hours per cubic meter per year, and down the bottom we have 0. And to the right-hand side in the picture we have 400,000 cubic meters of warehouse volume. And what I've attempted to do here is draw two graphs. The graph in the middle, this is the blue one, is what I call average practice. You can see it there. And the next graph down is what I have called best practice here. Now, the best practice graph is simply a polynomial regression analysis through some recorded SEC values for centralized low-charge ammonia systems. The average practice is a polynomial regression analysis through some other numbers, other SEC values for conventional liquid overfeed systems, okay? And then I've taken a really bad system here, more or less in the middle of the picture, and compared that with a very good system down the bottom of the picture. And you can see there that the difference in specific energy consumption, or SEC value, is a factor of 8. And this is at the high end of what is normally seen in practice. Normally, the difference between best practice and average practice is in the order of between 1.4 and 4 times. Now, this is, again, an unusual practice here. That little green star down the bottom of the picture there, the bottom meaning the bottom left-hand side, you can see a little green star there. This is an installation that was put in May last year here in Australia. And I call that super practice because that installation is 40 to 45%, let's say that, below what I call best practice here. Admittedly, this gentleman is very good at managing his cold store, he's good at closing doors, but it is nevertheless quite an achievement, much, much lower than what up until now I personally call best practice. So in terms of energy conservation potential, and this is taking a, shall we say, a big macro look at the global refrigerated warehouse industry, if we take a 100,000 cubic meter cold store and we take the difference between average practice and best practice, we see a difference of a factor of 4. And this is representative of the energy conservation potential that we have in the refrigerated warehouse industry as a broad average globally today. In Australia, for example, more than 90% of existing refrigerated warehouses, and we have more than 100,000 refrigerated warehouses in Australia, do not meet best practice. We know this. Here's a financial viability example. What this is it's meant to illustrate how big the difference is in money between an average practice warehouse and a best practice warehouse. So typically the refrigeration system for a warehouse like that costs $3 million in Australia. Best practice energy consumption is about 1,500 megawatt hours a year. Average practice energy consumption is about 5,500 megawatt hours per year. And that difference is money, is about $800,000 a year. Now this is based on an electricity price of about 20 cents per kilowatt hour, $200 per megawatt hour. And if you divide 800,000 into 3 million, you get about 3-4 years. Now, even if you were paying less than that, like let's say $100 per megawatt hour, it is still a lot of money, and it would still provide a reasonable return to pick a high energy efficiency refrigeration system, because it frankly does not cost a lot more than a conventional liquid overfeed system. So is a conventional plant worth keeping? Well, personally, I think not. This is another real life example. This is actually a replacement. You've seen this graph before in the beginning. This is a single stage economized screw compressor plant, which cost nearly $400,000 a year to run. You can see how the figures are made up there. A replacement plant, which is a centralized low charge ammonia plant, will cost $1.2 million. And that plant has got annual operating cost of $115,000 a year. We know this because this client already has a plant like that. And this is what I've circled in a yellow circle, more or less in the middle of that graph, okay? The graph to the left in the picture. So the client goes into this with open eyes. He knows what he's going to get when he replaces the plant, and he knows that his payback will be less than 5 years. Now here's another example. This is the replacement of an HFC 404A system. Here you see pictures of the 404A installation as it was. A very small facility, approximately 3,200 cubic meters of refrigerated volume. It's a food service business. The Freon plant had been lying dormant for a couple of years. You can sort of see that in the right-hand picture. It looks decidedly unused. This was replaced with a new dry expansion ammonia plant that was pre-assembled in the workshop. You can see on the left-hand side there, you see the prefabricated plant room. The ammonia inventory is quite a bit less than 250 kilos. On the right-hand side, you see the evaporative condenser. And this reduced the SEC value from 206 to 68 kilowatt hours per cubic meters per year. Now, the 206 value is recorded, or was recorded, over 5 years prior to the Freon plant being shut down. So that value is quite real. And the 68 kilowatt hour per cubic meter value was recorded over a number of months with the SCADA system for the ammonia plant. At the same time that the plant was converted from ammonia, from Freon to ammonia, it was also expanded by 40% to approximately 5,300 cubic meters. Yet the reduction in the monthly electricity bill for the customer was $10,000. Now, interestingly, that reduction in electricity cost per month is enough to pay the installments on a commercial loan over 10 years at 5% per annum to finance the purchase of the new plant. Now, what this means is that the investment is cash flow positive from day one. In other words, he can save money, the client can save money from day one, but it will require the client to have a healthy balance sheet so that he can go to the bank and borrow the money. So here's another real-life example. To my knowledge, this is perhaps the first time this has been established. So what we see here is two refrigeration systems that are conceptually identical. Both systems have 4 reciprocating compressors in two-stage mode, 2 low and 2 high. This plant that you see here, where the number 22 is, this is a 22,000 cubic meter warehouse that was installed approximately 10 years ago for a transport company here in Brisbane. That plant used 1.4 times best practice. The SEC value was 1.4 times best practice. This gentleman disposed of that plant and bought a new plant with a refrigerated volume of 44,000 cubic meters. That's the blue cross there. And that new plant, which, as I said before, is conceptually identical to the old plant, uses 0.97 times best practice. The only difference between the two plants is that the old plant was liquid overfeed and the new plant is dry expansion. So the effect we see there is a 1.3 times reduction in SEC value, and that is caused by the elimination of heavy liquid in the suction line network of the plant. Here you see some images of the new plant. The 4 compressors in the bottom right hand of the picture, the SCADA system on the bottom left hand side, and some pipe work and some valve stations, etc. Now, the ammonia inventory in this case is 350 kilos because it is all ammonia. We don't have a glycol loop for the medium temperature. It is all ammonia dry expansion. So the inventory is a little bit higher than the plant I showed you before, where we had a glycol loop for medium temperature. Now, I think I'm just about running out of time, so I'll just go through this quickly. All these red dots, they represent SEC values from a major cold store chain in the US. And just for fun, I have drawn the little green star from before, and you can see the green star occupies a very lonely place in the bottom left-hand side of this graph. Again, the graph shows SEC values on the vertical axis and refrigerated volumes on the horizontal axis. And that difference, in my mind, is quite staggering. Now, that plant is installed. This is the Green Star plant. This shows an image of the Green Star plant. It is a packaged engine room again on the right. And the operator basically installed a PIR panel box inside an existing shed. And the shed you can see there and in an aerial photo. And the final real-life example is a chap who consolidated 3 Freon-based facilities into one and reduced his electricity bill from very close to $1 million to $500,000 a year, while at the same time having a significant increase in refrigerated volume. The ammonia inventory is 472 kilos for 60,000 cubic meters of refrigerated volume. The 500 kilos is a threshold in Australia. If the facility has more than 500 kilos of ammonia inventory, it is classified as a dangerous goods storage facility, which means it is subject to additional compliance requirements that cost additional money. This is cold leg air distribution, but I don't have time to get into that in details. So just one open question: why are we not designing for best practice energy performance? It is in the best interest of all stakeholders. Why is it not common practice? I'll leave that question with you. Why is there no best practice energy performance benchmarking? There is that sort of benchmarking in some countries, but they're few and far between. We don't have it in Australia. What is the capital cost difference between best practice and average practice? No more than 15% in my experience between a liquid overfeed system and a centralized low charge ammonia system. So that 15% has a very quick return on investment. And what proportion of the total life cycle cost of a refrigeration plant does the capital cost of the system represent? If you don't know the answer to that question, I'll volunteer the answer here. It is approximately 10%. In other words, the cumulative operating cost of a refrigeration plant is 10 times higher than the initial capital cost. Yet in the vast majority of cases, the buying decision is based on the capital cost of the system and not the cumulative operating cost or life cycle cost. And why is it often the entity that understands the least about the refrigeration technologies that get to make the decision about what technologies are to be applied? This is really a strange question. In the vast majority of cases, in Australia anyway, this is what happens in practice. And I'll just leave you with that question. And if you have any questions, Devon has promised to handle those. So thank you very much for listening.
Very much. Please stay on. We will ask a couple questions. The summary of your presentation basically highlights all the important points. And I believe the fourth question that you have listed provides the answer to the first. Why is it not happening? Why is the energy best practice not the commonplace? Is it because of the initial cost of the plant is really the only, or one of the only, or one of the key decisive factors when making a decision about technology being deployed, or what's really holding this back?
I think there's a couple of things. First of all, there's a lack of awareness about how different or how big the difference in SEC value can be between one plant and the next. The other element, of course, is that in many projects where we have the interaction between a developer and a builder who builds the facility and a refrigeration contractor, the builder typically takes the decision on the basis of the lowest capital cost. So if a conventional centralized ammonia plant with liquid overfeed happens to have the lowest capital cost, and nothing else is said about what kind of plant the client who pays the electricity bills wants, then the builder will accept the lowest offer, and that lowest offer can very well be the plant that delivers the highest life cycle cost. The third aspect, and I haven't really discussed that in detail, is that it is very difficult to model the energy performance of liquid overfeed systems, and that is because currently there is no correlation that will predict the pressure drop in wet risers when those risers are in flow reversal. Now, what this means is that when the wet riser in the suction line reaches what we call a Coulthard-Larsen number below 3.2, then it is characterized by flow reversal, and there's no correlation that will predict the pressure drop at that point. The more oversized the riser is, the worse the pressure drop in the riser will be, and the higher the penalty in the plant room will be. The wet riser pressure drop can be anything up to 60 times greater than the pressure drop in a riser that carries vapor only.
Stefan, thank you. We have a couple of questions from the audience. I will try to go through several of them, if I may ask for a brief answer. The first question is from Mark Gatako from GNQ, and the question is there a difference on the maintenance cost between the low inventory NH3 refrigeration system and the pumped ammonia refrigeration system?
Now, this is me as a contractor, and not everyone has the same experience. We are now only servicing centralized low charge plants every 2 months. We used to service them once a month. We don't anymore. The annual maintenance cost is in the order of 1.5% to 2% of the initial capital cost of the system for an average size DX ammonia system, and that excludes water treatment costs. For liquid overfeed plants, we find that the maintenance costs are somewhat higher, 1.5 times to 2 times higher than it is for centralized low charge ammonia plants. We simply have more call outs on liquid overfeed systems.
Thank you, Stefan. Next question by Anshu Kumar, UNICEF. What is the minimum plant capacity with ammonia?
The one I showed you, I think it was real life example number 3. That one there is borderline. 5,000 cubic meters of refrigerated volume, 50 kilowatts low temperature capacity, 50 kilowatt medium temperature capacity. Any lower than that, and transcritical CO2 with adiabatic assistance will be more competitive even over a life cycle of 15 years.
Thank you, Stefan. And final question. We know that you have a project currently under construction or maybe being commissioned in Malaysia. Can you tell us in brief what's the status of this first deployment in Southeast Asia? And the second part of this question is, are you open for business in Philippines if there is an interest for this technology?
Well, first of all, on the Malaysian project, we had a lot of setbacks because of COVID. The plant has been pressure tested and leak tested. And then it was discovered that the monkeys have gotten into the cables. So there are some cables that need to be replaced before we can actually get on with commissioning. As to whether we are open for business in the Philippines or in Asia generally, not until we are over this COVID situation, unfortunately. It is simply too difficult. We are banned from traveling anywhere from Australia. We need special permits from the government and what have you. And there are no flights, and the flights are just too expensive, so it is just too hard at the moment. That's just the sad state of affairs.
That's reality. And the monkeys in Malaysia, very interesting challenge to the low charge ammonia system. Thank you very much, Stefan, for sharing all this information and the best practice with the industry. I think it was fantastic. We have several more very technical questions that we will share with you over email if you may find a little bit of time to provide answers as we go. So, Stefan, thank you again very much. It was very good to have you here.
Thank you. See you later.
See you later. Devin, go ahead, please.
So we have Mr. Cesar Lim, who is an expert in the ammonia, in the use of ammonia refrigeration systems and the use of ammonia as a refrigerant, especially in the Philippines. And he is with us right now. He's going to talk a little bit about the history of the safe use of ammonia as a refrigerant, but also some of the issues that the industry is facing today. So let's see if we have Cesar on with us now. Cesar, can you hear me?
Yeah, I can hear you. Okay.
Cesar, how are you today?
I'm good.
Okay, great. Thank you very much for joining us. And we know that you are a very knowledgeable and true expert on the use of ammonia in the Philippines. So please go ahead and take it away with your presentation. We're very much looking forward to it.
Okay. History of safe use of ammonia and as a refrigerant in the Philippines. So history of the use of ammonia in the Philippines started in the 1890s when San Miguel Brewery used ammonia as for the refrigeration system in its brewing process. Insular ice plant and cold storage in Luasang Bonifacio was the oldest facility that produced black ice and also store unpasteurized San Miguel draft beer in the 1900s. And this is already gone. It has to give way to the MRT1 line in 1984. All black ice plant before World War II were using ammonia as refrigerant. Most of these were built by Coppel Inc., the oldest refrigeration company founded in 1904 in Manila, Philippines. Coppel was using the refrigeration technology of Frick for its ice plant and cold storage and brewing process and food processing. Low speed 300 to 400 RPM reciprocating compressors were used, usually Frick or a York heavy duty compressor. It's a 2-piston compressor. The oldest ice plant in the Philippines was Luz Ice Plant, also known as TP Marcel, using low-speed York and Frick compressors. One of the oldest ice plant still in business in the Philippines is also Mandaluyong Ice Plant, owned by the Samson family in Shaw Boulevard, Mandaluyong. After World War II, Pacific Star, owned by the Cantada family, using ammonia leaks are normal occurrence in old ice plant due to poor maintenance record and the use of ammonia refrigerant with a purity below 99.95% or refrigerant grade. Usual accident happens due to untrained plant personnel in ammonia safety. It also happens during the manual purging of air in the refrigeration system as they don't use automatic purger. The biggest ammonia accident happened in 1978 in San Miguel Polo Brewery due to liquid ammonia leaks in its brewery cellar cooling system. 3 engineers died at said accident. The problem is actually poor refrigeration preventive maintenance and the use of low-grade ammonia refrigerant. The reaction of San Miguel management was to convert the cellar in 1979 using propylene glycol as secondary refrigerant, and the refrigeration system is converted into Freon or R22. The solution was short-lived, but the system was not efficient. In 1983, the R22 system was junked and replaced with the efficient ammonia glycol chiller system in its fermenter and storage tank. In 1989, almost all of the big refrigeration plants in the Philippines were using liquid overfeed, which is cheaper to build and efficient than the flooded system. In February 3 this year, the biggest ammonia to date accident in terms of 96 persons were hospitalized due to ammonia fumes, and 2 employees died in the TP Marcelo ice plant incident due to the probable metal failure caused by ammonium hydroxide, a corrosive chemical produced when ammonia mixed with water. This is due to the practice of not using refrigerant-grade ammonia. And in 1993, I told the owner, the late engineer Tobias Marcelo, to use refrigerant, but he didn't follow my suggestion. In year 2002, San Miguel Group started our PET packaging plant. We envisioned to use low-charge ammonia chiller for the 3 facilities in the Philippines and another 3 in Southeast Asia. We have 2 types of system, the pure package chiller using PHA and skids, and the hybrid package chiller with PHA evaporator and evaporative condenser. We have done this hybrid because of poor water quality in the Philippines. We have GNQ, the only local manufacturer for these 2 types of package chiller, and still manufacturing it in the Philippines until now. Well, industry training in ammonia and CO2 refrigeration in the Philippines. Ammonia and CO2 refrigeration training in the Philippines is 0. In 1993, San Miguel Brewery decided to send 2 of its refrigeration engineers to study further industrial ammonia refrigeration system and operation in the Whole Training Center, Northwest Kent College of Technology, Dartford, Kent, UK. In 1993, San Miguel Brewery started the Brewery Engineering School to train engineers in ammonia refrigeration operation. ASRAE, Philippine chapter, planned to set up an ammonia refrigeration program similar to Whole Training Center, but until now it is just a big plan. The challenge is the financing of an ammonia CO2 training center, as we detail a lot of costs for our ASRAE chapter. We need the refrigeration manufacturer to support our dream, the center like the Whole Training Center in Dartford, Kent, UK, and the Garden, similar also to the Garden City ammonia program in Garden City, Kansas. The refrigeration industry has no program in training engineers and technicians in either ammonia or CO2. Our group had an idea, but we need the support to fulfill our dreams of 20 years. So for the ammonia safety program, we can conduct this similar to what Ammonia Safety Training Institute is doing in the US. The video safety training can be done as soon as I have attended the training in Baltimore, Maryland in June 2008. We can do the emergency response training, which we have done with our clients, and we can share this training to the industry. Thank you very much.
Cesar, thank you very much for your presentation. Yeah, sorry about those connection issues, but I think we heard some of your main messages very well. I'd like to ask you a few questions, if you don't mind. Can you hear me?
Yes, I can hear you.
Yeah. So you mentioned that there was a training initiative that you were working on for the past few years with ASRAE, the main hall, I believe. Is that still ongoing today, or is that not happening?
It's still a plan because we have problems on financials, and we need manufacturers of compressors and the others to help us set up that training center. So we need for natural refrigerants. That's it. Ammonia and CO2 if possible.
You know, the presentation that was before you, Mr. Stefan Jensen from Australia, was talking about reducing the ammonia charge in the system by a significant percentage, and this having multiple effects on energy efficiency and safety. Do you see a big potential for low charge ammonia systems? Other than training, training is a big issue, but for the systems themselves, do you see potential for those in the Philippines?
Well, the problem actually is, as Mr. Jensen had said, that the problem is the first cost. The Filipino businessman would still go to the lower cost technology. That's the biggest problem, because we were trying to do that, but but didn't push through because the clients are always comparing with the old system and liquid overfeed. So that's the biggest problem.
Yeah, one thing. Yeah, finance for the training and for the systems themselves. One thing Stefan Jensen mentioned is that with a loan, you could and the savings that you would get from the energy efficiency of the systems from day one, that would almost offset the cost of those loan payments. Does that sound like a good opportunity for people who might not be able to afford these systems?
Yeah, that would be a good opportunity if the clients are open-minded. That's the biggest problem that we have in the Philippines. Because they would always compare to the first cost of their competitors.
Yes, knowledge, raising awareness and spreading knowledge is, I think, one of the main missions of our project here with the CCI-Hub. Thank you very much for your presentation. Can you tell us a little bit, just to close things off here, what are you working on these days with respect to ammonia refrigeration technology? What are you working on currently?
We are building a 10,000 pallet position cold storage in Cebu, and it can be expanded to another 8,000 on the second phase. So we'll be cooling down by next month. We'll cool down the the cold storage, and it would be operational and completely test and commissioned by June. So that's what we're doing.
Great.
And we have another project, but it's for an abattoir, slaughterhouse, and we're not yet sure if, because the budget is a problem, we need an additional of about 30 million for the budget of the owners.
Yeah, so multiple projects ongoing today. Okay, thank you very much, Mr. Cesar, and thank you very much for your presentation. We'll say goodbye for now, and we'll talk to you again soon.
Okay.
Thank you.
You're welcome.
Yes. Okay, great. Okay, so yeah, we are very happy to have Mr. Dion Leenhouts, David Blankley, and Criseldo Casilan from GEA, GEA, who will be speaking to us today about cold chain technology in the Philippines and some of the best practices and safety that deal with these systems. So Dion, I believe you are going up first. Whenever you're ready, please take it away.
Okay, sure. Well, good afternoon. My name is Dion Leenhouts, and I'm working for the GEA Refrigeration Division as a sales consultant for refrigeration installations and heat pump systems. Today, I would like to share with you our experience on what's going on in the global cold chain industry, and the goal is to show you what the developments in this industry are and what the future considerations are in terms of energy consumption and CO2 emission reduction. In other words, the cold chain. So let's look at what we're going to look at today. So first, I want to discuss quickly what are the global industry trends and what the market is saying, and what are they expecting from us for their business, and what it means for us to design a refrigeration system. We have to take all these future considerations into account. Then we are going to look at the importance of the rising energy and operating costs, which are going on all over the world, especially with the new legislation, what will come to us. And then we're going to look at the heat loads, because there it all starts. It's the quick win to design a very efficient installation. Now let's also see what the heart of the installation, which are the compressors, what impact they have on the operating costs. And further, I would like to show you what it all means for the air and temperature distribution inside the cold store. Because these cold stores are getting bigger and bigger and bigger, and air and temperature distribution gets more complicated. Then I would like to have a quick look at what we normally encounter in terms of design on natural refrigerants, and that can be ammonia and CO2. And then I would like to have some final words on the CO2 emission. So what does the industry say? Cold chain logistics and refrigerated warehouses, they are growing. They're getting bigger, and that is because more people want to have high quality food products. Secondly, and to stay competitive for all these customers, they have to look for logistic solutions where they reduce energy and minimize costs. And nowadays, the automatic warehouse offer the best advantages. Completely full automatic warehouses. And they are called the ASRS system, the so-called automatic storage and retrieval systems. And the market is growing and growing every year all over the world, and especially in Southeast Asia. And the automatic high bay cold stores are the future in cold chain logistics. So we, as a company that is designing refrigeration installations and perhaps heat pumps for them, have to take these kind of things into account. So what does that mean for us? So in any way, it's changing. Customers would like to have 100% tracking and traceability. Not only for legal purposes, but also to satisfy their customers. And things like that can be included in our software. There is a tremendous focus on energy consumption, and everything focuses towards high bays at the moment. And quickly, what is a high bay? You see a little picture of one being built there. They are around 40 meters high, 100 to 150 meters long, and 60 meters wide or so. They're quite high and big, and fully automatic. Yeah, the point is, because of these high buildings, the air distribution is getting more and more difficult. Yeah, you have to get all the air nicely distributed in these high bays. And therefore, we developed, or there are CFD calculations and simulations that can improve this air distribution and where we can reduce the energy consumption. By the way, a CFD is a computational fluid dynamics. It's a simulation tool where we can predict what the temperature and air distribution throughout the high bay is going to be. Very handy. So now you see here on the left, you see there this big crane, and that is what an ASRS system, generally is looking like. It's a big crane or cranes, some maybe 4 or 5 in one room, going up and down, and from back and forth all the time. And therefore, it has an impact on our air distribution, but also on our heat loads. So the heat load calculation should be taking these big cranes into account. And in terms of energy consumption, we have to have a very narrow balancing act between the evaporation temperature of the coolers and the compressors. And sometimes this air distribution system sometimes require a specific solution. Now, what do we now take into account when we're gonna design a plant like that? First of all, it's the personal and the product safety. That's the most important. What kind of natural refrigerants are we going to use? Are we going to use NH3 or CO2? It depends on all kinds of preferences. The other thing is, of course, HACCP and product quality. Everything has to be trackable, measurable, and traceable. And for that, we need a very good operator training, which we come back on later on. One of my colleagues is going to talk about that more. The other thing, and it's mentioned a couple of times this morning, operating costs, OPEX, and total cost of ownership. Yeah, we want to have high efficient compressors, especially in part load. Because part load, when installations are running in part load because the heat load is not calculated very well, the compressors are not really, none of them is not, they are not running fully efficient in part load normally. Yeah, then of course the right cooler selection and air distribution system. And we need to discuss what are the tariffs for electricity. Do you have a difference in night and day? Because this information also has a big impact on our heat load calculation. For instance, we could advise a customer to invest more in bigger compressors, but that they are running less, and that they are running only in low tariff times, for instance. Oh. So, yeah, you've probably seen this picture before, but it is a very important one. Most of the costs customers are paying is not for the refrigeration installation of our compressors or whatever. It's what is beneath the surface. It's the energy. Yeah, the investments is only a small part compared to the complete total cost of ownership. Now, the last thing, of course, and that is also very important, is what kind of reliability do we need? If a customer has for $50 million worth of goods in his high bay cold store, you want to make sure that nothing gonna happen with this with these products. So what about spare parts? How do we have spare parts around? Do we have a local organization that can help us if something happens or something needs to be serviced? All these new design criteria are specified on this the new trends in the high base. Now let's look at the operating and energy costs for a moment. This is a very interesting little graph that says, what are we all paying for? What is the customer paying for? Or what is an operator of a manufacturing plant paying for? Except for the raw materials, of course, because that's his business. But he pays much, the biggest costs are the energy and the utility costs. And the energy and utility cost, one of them is, of course, the refrigeration installation, and it's not the smallest. If we look at it, we have some different industry sectors here that indicates how much of the electricity is used for refrigeration. And it goes up from 25% to 85% for cold storage. Yeah, the big cold storage, most of the costs are for the refrigeration installation and the electricity costs. So we have a responsibility to bring these costs down. Now, so first we're going to look, where are these costs located? Now, then we start of course, with the heat loads, because there it all starts with. As you can see, two parts of heat loads are important. So that is the transmission. There's nothing much we can do about it because, it's dependent on the climate and the way it is insulated, how the building is built and everything. Another big one are the product loads. Do we have a very smart logistic system? It's something you can discuss. It's not wise to bring temperatures of products down in a very, very big cold store. It's much more efficient to get the products already on a good temperature in the freezers. It's much more efficient instead of doing it in a cold store. So we would like to advise that you bring your goods in at the storage temperature. And you see two other things. That is here, the additional load and fan load. The additional load, those are the big cranes and conveyor belts and robots and all that kind of stuff that's driving and moving around in these cold stores. And then, of course, the fan load, those are the big coolers. We're talking about big coolers here because one cooler could be approximately 300 to 400 kilowatts and give a lot of fan load. So, what are we going to do with these heat loads then? So, first of all, we need to calculate the right load, but the right load is very, very subjective. So we have to look at part loads depending on transmission. Well, we're here in Southeast Asia, and the climatic conditions are not changing that much. There's not much of a summer and winter condition in the Philippines. Product type and intake temperature. Yeah, what is the intake temperature? Yeah, try to get that done in a way that it's brought on a lowest temperature as possible in an efficient way. How many cranes and what kind of cranes are going to be installed, and how many conveyor belts and how are they running? And what's also an interesting one to look at is the operating time of the compressors. The less the compressors are running, the bigger they're going to be. So, but that could be a good solution, as I said earlier, that if there is a big difference in the tariffs, let them run at the cheapest time of the day, but make them a little bit bigger. But that's an investment you need to make, and it needs some calculation to find out if it pays back. Now, what are these, because we're talking about electrical costs and operating costs, what are the main consumers? Well, of course, that's typical, the compressors. And in a high bay situation, we call them a high bay, these high-rise logistic centers, the compressors are by far the biggest. Condensers, not that much. But the air coolers, they also are much higher than you would expect. Big air coolers, lots of air, lots of fans. Let's say for one of the cooler like this, you have a couple of fans. They are 7.5 kilowatt each, so you are easily, on an average one, you are looking at between 150 kilowatts and 200 kilowatts of electrical power of all the coolers in a high bay. So that's quite significant if you look at it on a yearly basis. Now, what can we do on these compressors? First of all, it's balancing the evaporation temperature between the coolers and the compressors. Do we invest in cheap coolers, smaller coolers, but then we have to bring the evaporation temperature down, and that means bigger compressors. The other way around, if we have big coolers, then we could use smaller compressors. So it's a balancing act. As I said before, what times of the day the compressors can run, and certainly is a smart sequence and capacity control system. And we have some nice solutions for that, and my colleague is gonna talk a little bit or point them out, because we need to prevent to have compressors run in part load, because part load is making the compressors a little bit inefficient. And what are we going to select? Are we going to use screw compressors for big installations? Yeah, we're looking at an installation typically between 1,500 and 3,000 kilowatts. Or do we need a nice combination between piston compressors and screw compressors? What's done here in Europe a lot is a floating condenser pressure. But yeah, in the Philippines, that's not going to bring a lot. Oh, wait a minute. That was what happened here. Sorry.
Yeah, Dion, no, we're taking a look. Yeah, it looks like you got the correct slide. I think it was on the slide before. So yeah, we have you on the compressors.
I'm at the right slide at the moment, I think. Yeah.
Okay.
I can continue, but Yeah. So floating condenser pressure is not the best solution for the Philippines, I think, because there is not enough difference between the summer and winter and night and day. It's hot in the morning, hot in the evening, hot in the spring, hot in the winter. In contrast, not in Europe, there's a much bigger difference, and we can make better use of that. Yeah, and of course, regular and proactive maintenance, not waiting until something is broken or waiting until something is not running as it should be, but be proactive. And there is software for that to keep a close eye on that. And then you will keep your compressors, let's say, up to date. And look at the prices of the power consumption of the compressor. Yeah, that by far the biggest one. And we're looking at quite some numbers on not such a big compressor, what it is costing in 5 years. Yeah, you're paying easily €500,000 euros or dollars for an average compressor in 5 years. So it's really good to have a look at that. Yeah. So, and a few words on air distribution and product safety. As I mentioned, traditionally, yeah, we have these nice coolers hanging here on top of the cold store and blowing over the product. And what you see then, it could work, yeah, but now they're going to get bigger and longer. Let's say the maximum airflow of a cooler is around 70 meters, 60 meters, depends on the cooler supplier. But when you go to 150 meters, you get this kind of effects. As you can see on the right bottom, you see these secondary flows going on in your cold store. And what's going to happen is nicely shown here in a CFD calculation, is that you're going to get quite a big temperature difference throughout the room. It's very nice to see that in a simulation. And maybe it's not such a big deal, but you just go deeper in evaporation temperature and use then an extra energy to get all the temperatures within the range. But it's not the perfect solution. Yeah, so the airflow of the fans, yeah, have to be so much that they have to reach the other side of the room, preferably. So that's a lot of power. Yeah, and there are barriers and all kinds of other stuff. Let's say that is causing not a very nice flow of the air. So yeah, so if these stores become big, and they become bigger, they really become bigger, then they need high-speed fans with high driving power. So another nice solution would be to have, today I heard the word already, it's the cold lake principle, where we go down, but with a low fan speed and with a low external pressure of the fans. We bring it down, and then we go up through the products. But it's very good to simulate that to determine what would be the frequency of the fans there, because we do not want to overdo it, and we want to make it the fan speed as low as possible. And for that, we are using these CFD calculations to make sure to the customer that all the temperatures in this room are within the range. So that is it's a very nice system to make with a relatively low temperature absorbed power of the fans, and have a nice even distribution of temperatures here. Of course, it's not always possible to do that. Yeah, your cold store needs to be suitable for that. Yeah, you need to be able to have a free downflow of air. We're now at one end and we are looking up, and we see here the fans of the coolers blowing down. That has to be completely free, and the air must flow nicely and not to be disturbed by the stacking cranes. And we need some free space under the pallets, like you see here, on the right one. So we need to make also during the construction of the high bay, you need to take that into account, that is a free flow of air. Now, if we're going to do that nicely with the CFD modeling system, yeah, we can absolutely make it minimize the fan speed, and we can reduce fan power. Yeah, and as I said, we use this CFD modeling. And you see more and more customers falling back on this system to make sure their air flows and air distribution in their big stores is perfect. Now, what we normally use on these concepts, so we have the coolers looked at, we have the compressors looked at. Let's look at the whole thing at the moment, basic concepts. We have here the basic NH3 system. It's a pump system. It's not with direct expansion, but it's still a pump system. Yeah, that's always the safest solution there is. It's the cheapest solution. It's the safest solution in terms of it's simple, reliable, energy efficient. However, there are circumstances that customers are not so happy with the amount of ammonia in it. There can be quite a lot of ammonia in it, and of course with the DX systems that could be reduced, but yeah, sometimes they don't want to have any ammonia or not ammonia in the cold store itself. So then we have to look to another system, and that's here this is a very safe and robust system, CO2 working as an evaporating brine. It gets a little bit more complicated because you have some extra condensers and cascade condensers here. It's a bit more expensive. But here you will have only ammonia compressors in the machine room. Yeah, with underneath a pump system here that pumps CO2 to the coolers and it returns back again. And the last bit we use a lot are the CO2 and NH3 compressors, a so-called cascade system. They work in cascade, so you have two types of compressors here, CO2 compressors, and these are subcritical, so not transcritical, but subcritical, and high-stage compressors that act actually as a condenser for these subcritical condenser. So these are basic concepts, of course, and they are going to be every single distribution center we're going to look at. We're going to look at what is the best. You have to look on what is the best solution because every story is different again. Now, and some last words, because it's not only about energy consumption and it's not only about reducing operating costs. It's not only that awareness we need, but it's also about reducing the CO2 emissions. As we know, in 2019, most of us signed the Paris Climate Agreement, and we have some ambitious goals to bring down the CO2 emissions. So we have to think on reducing these energy consumption. Or to reduce the energy consumption based on this Paris Agreement. And also the Philippines has signed and also has some ambitious goals for that. So not only that, we could expect in the future rising energy tariffs and CO2 taxes. That's going to be happening in the future. So investments based on the total cost of ownership are getting more and more and more important. Well, thank you for listening.
Dion, thank you very much for your presentation. It was very, very enlightening, especially when you're talking about the automatic storage and retrieval systems, which we know are becoming popular. Many of them are being built today in the Philippines, and also the use of natural refrigerants and why it's important. But we also would like to introduce now your colleague, David. Well, you're based in the Netherlands. He's based in Lisbon, Portugal. So we'd like to see if David is on right now as well, who is going to be speaking about Gaia's Omni technology, I believe is control software. David, can you hear me?
Yes, I can hear you. Thank you very much. Yeah, I'm here to talk about, and really on the back of Dion's excellent presentation, where it's reinforced, in fact, that we need to have efficient equipment and very efficient design. And in addition to that, we really need to have a very efficient control system. And at Gaia, we've developed a controller called Omni. It began its life really as a compressor controller, but we have continued that development really to enhance it, so it is becoming more and more a system controller. And the basis for Omni was really efficiency, that is driving the compressors in the most efficient way, but also communication. Because nowadays we have so many ways to communicate with internet and Wi-Fi and our mobile phones. So we have embraced that technology and incorporated it in our Omni controller. So for instance, a quick customer report. So here's a control system. Here's our Omni controller. Could be mounted on one of our compressor packages. It comes with a QR code where it's possible to scan on your mobile phone. And that would give you instantly the operating conditions on that machine. So you only have to have a Wi-Fi connection to be able to see how your compressors are operating, and even by your mobile phone. But Omni is more than that. In terms of the compressor, it's really looking at giving customers peace of mind. So also lowering things like maintenance costs. So we look at features like automatic maintenance alerts, dynamic maintenance, which means we're constantly looking at the operation of the compressor over a period of time to see if there are any small changes that are occurring that might need some attention. It's very configurable, so the customer can actually see the data that he wants to look at. And there is everything available within the Omni control as to what's happening on your compressor. And paperless reports. So consequently, if we need a service report, or we want to check when the last service was done, or see what the engineer actually found, if he made any notes, that can all be stored on the Omni controller. And network communication. As I mentioned, communication in this modern day and age is so easy, but also we recognize that customers also have their own protocols sometimes. So we built into the Gaia Omni some standard communication features. So if you're using Modbus or Ethernet or Modbus RTU, or you have an Allen Bradley PLC, which is controlling your plant, Omni can communicate with it. And we have other options as well, like Profibus or Profinet. So we try and cover the spectrum of communication modules that are current in the world today. We have other features like Omni Link. So really, Omni is fully accessible anywhere you have a Wi-Fi connection. And Omni Link allows the operator to make changes from remote locations. So he can direct data to his computer. He can upload files, for instance. He can make automatic backups. And he can update the program and configuration. So as Dion described in the store, maybe we have a change of product, and we can wish to change the evaporating temperature in the store to more suit the product. That can be done completely remotely via the Omni Link method. Omni also incorporates this key driver, which is efficiency. So we developed a smart sequencer. And Dion also mentioned what type of compressor you're using. Well, sometimes it can be a combination, screw compressors and a piston compressor working on the same system. That piston compressor can be therefore things like weekend duty. Very often when the store is not operating at weekend, then why run a big screw compressor set with a very large motor when you can do that duty with a much smaller machine? And the smart sequencer also looks at the size of the compressors, as I mentioned, and it will balance those machines to give the most efficient operation at any given moment in time. So if we see the opportunity to switch a large drive motor off, replace it with a smaller machine or a smaller drive motor, then Omni will automatically do that for you in the smart sequencer. The same goes for chillers. For instance, this shows 3 chillers. They can be of different sizes. It can be chilling glycol. We have a buffer tank for the control. And in this sequence, again, we're looking at maximizing the efficiency. So we have compressors that go below 50% capacity, for instance, then we can decide to turn them off. We can decide to increase compressors speeds to give the best combination at any one time to suit the actual conditions in the plant and the actual duty that's required. It's live and it's dynamic. I mentioned Gaia is more than a compressor controller, so we can add the Omni as a system panel, whereby we can connect all the compressors and we can start to connect other features of the plant. So pumps, condensers, and even air coolers. And we do that by a feature called the Smart Connection Box. So on each of these individual components, we have a Smart Connection Box which takes in data and delivers that to the Omni system panel. And we're already working on algorithms to enable artificial intelligence to be included in the Omni. It's already there to some degree, but this is really an opportunity to have real-time anomaly detection. So as soon as we think that something might be happening within the plant that we see as a small abnormality, then that can automatically be detected and automatically be delivered to the service organization and the operator at the same time. We live in a digital world, and we're encompassing all those features and things that can really help us develop further this control system to give you the optimum control. Thank you for listening.
David, thank you very much for that. You know, Gaia is supplying not just compressors and systems for industrial refrigeration, but it's good to know and learn about the advancements that you're making in control systems as well, and taking advantage of everything that you can do today with data and analytics to increase efficiency, preventive maintenance as well. So thank you again, David.
Thank you.
So now we are going to be connecting with Criseldo from the Philippines, actually, from Gaia, Pilipinas. Criseldo, can you hear me?
Yes, Devin. Can you hear me also?
Yes, we can hear you loud and clear. You're good to go. You're going to be telling us a little bit from your perspective about ammonia safety and best practices. So please go ahead.
Okay. Thank you very much, Devin and David also. So I will be, good afternoon and good morning to everyone. I will be sharing with you based from experience and some international and local codes about the ammonia safety and best practices. Okay, so it is important for people handling ammonia to familiarize and understand how the system works. training of people handling the plant should be made aware of the probable hazards and how to treat it. Safety training should be done prior to handover of the plant. It is advised that an annual training be conducted to personnel handling the plant. This will serve as a refresher to the system operation and maintenance. Also, should there be incoming new employees, training should commence as soon as onboarded. Would there be any activities, for example, such as repairs or installation works, safety guidelines must be discussed both with the client or the representative and the contractor. Okay, ammonia machine room. Refrigeration, machine room, machinery rooms must be constructed in accordance with the building code intended for ammonia system applications. Signages as well as other pertinent information should be visible. And also, authorized personnel are allowed should they be entering the machine room. Okay, pipe marking. Pipe marking should be installed for accurate identification for flow. This is also to distinguish the type of medium present in the pipe as well as its characteristics, the physical state, liquid or gas, the relative pressure, whether if it's for high pressure or low pressure, the pipe service, for example, if it's for the hot gas line, suction line, or condensate line, and also the directional flow. Okay, bulb tagging is also included. It should be installed also for proper identification and for locating it easier. This should as well be in alignment with the PNID, piping and instrumentation diagram for accuracy. So you can easily locate the valves that you will be doing some activities on. Okay. For this slide, it shows the information of the equipment, the set points for the alarm, and also records of past faults should be kept. So it's sort of a history should there be some activities done to an equipment, be recorded. And then also what actions, what solutions have been made to it. Monitoring should be done to ensure that equipments on the plant are on the permissible operating conditions. So the settings. Okay. Ammonia pressure vessel. Ammonia pressure vessel should comply with the ASME Pressure and Vessel Code, Section 8, Division 1. This covers the design, fabrication, inspection, and testing during construction of the pressure vessel. Manufacturers producing pressure vessel shall provide data affixed on the nameplate. Also, the pressure vessel should have the safety features such as relief valve installed. So it should be sealed and set by the manufacturer. And also of the approved type and capacities. So if it's for a low pressure side or for it's for the high pressure side. Also, some local guides required permit. Normally here it's for an annual, so should be pressure vessel should be only used with approved permit. Also, the permit should be displayed in a conspicuous location, so easily seen, so that they know or people know by inspection that the vessel is still good to use. Okay. At least one ammonia detector for best practice shall be provided in the room or area. Alarms shall be activated whenever the refrigerant vapor exceeded the permissible exposure limit. So normally for people, it's around 50 ppm. Audible and visual alarm shall be provided inside the room to warn that when the alarm has activated. Access to the room is restricted to authorized and emergency responders only. In connection with the leak detector, purge fans shall also respond automatically to the refrigerant concentration detection system. Okay. Availability of personal protective equipment should be at site. An ammonia suit, chemical resistant apron, self-contained breathing apparatus or SCBA, SCABA, full face chemical mask, and chemical gloves. We would recommend, suggest, depending actually on the size of the plant, but a minimum of 2 units of SCABA or SCBA and a full face mask. And also during activities, we recommend of 2-person, a body-body system, should there be any handling activities for ammonia. Okay. Approved and safe methods. So prior to any activity, risk assessment and methodology are discussed by the plant authorized personnel and contractor to ensure safe and timely accomplishment of work. Work permits should be secured and coordination of other parties involved, such as management and production. We encourage that toolbox meeting should always be exercised. Okay. For this slide, familiarity of the plant site. Okay. So if you have some activities being done at the plant, you should know your location and the evacuation area. Also be aware of the safe route should an emergency happen or occur. Okay. So for this slide, all equipment shall be located in such a manner as to allow enough space to exit in an event of emergency. Emergency exits must be clearly marked and illuminated. No obstruction should be located in these exits. Also, based from the code, machinery room shall be equipped with light fixtures delivering a minimum of 320 lumens per square meter. Okay. Another best practice is each machinery rooms shall have access to a minimum of 2 eye wash or safety shower units. Establishment of an emergency response team should an ammonia-related accident occur. So they should have a response plan, first aid, and people with assigned tasks should the emergency happen. Okay. Accidental release. So should this happen, accidental precautionary measures are done. Use of PPEs, water dispersion, location of the source of leak and isolating it. Also, accounting of persons at the plant once at the evacuation site. And then activation of the emergency response team. So this happens should there be an accidental release. Okay, handling. Refrigerants and refrigeration oil not charged within the system shall be stored in a secured and ventilated area. Also, you should have the right trolley to be used. And disposal, drains, overflows, and blowdown provisions shall have an indirect connection to an approved disposal location. Discharge of chemical waste shall be approved by the regulatory or by the plant safety guidelines. Okay. Okay. Associated with safety is the maintenance. It's a process to keep equipment, tools, as well as instruments in a reliable working order. Well, main objectives are to avoid being inoperable, or should an emergency breakdown occur, make repairs. So importance of maintenance is being stressed out to reduce breakdowns, increase uptime, and promote overall reliability, and also to avoid disruption of production time. Okay, so generally, we have two types of maintenance. One is corrective and one is preventive. Corrective means the activity which are carried out after the occurrence of failures to correct the failures. This can also be referred as an unscheduled or unplanned maintenance. So some samples of that are cases wherein we have experienced some flooded compressor, burnt motor, or passing of bulbs. And then preventive maintenance, meanwhile, are activities which are carried out to prevent the occurrence of failures. So these are planned maintenance. Further classified into two: direct maintenance and monitoring. Direct maintenance are planned activities carried out to ensure instrument and equipment operations are followed. So samples of this are PMS for compressors, checking of alarms, checking of ventilation fans, lubrication. Next is monitoring, whereas by constantly checking the parameters like pressure, temperatures, and other data, major faults that are slowly developing can be detected in time. So these are some of examples of this one are visual checkup, checking for unusual sounds, cleaning of filter, and checking of pressures and liquid levels. So also we can use here the some SCADA or Omni to check if we are still operating in the proper condition. Yeah. Well, basically that concludes my presentation for the safety and maintenance.
Thank you very much, Criseldo. Thank you also to Dion and David from GEA for your very informative presentation. We have just run out of time, so I only have one question addressed to Criseldo about the situation on the ground in Philippines. When it comes to safety use of ammonia, when it comes to training of the technicians, what is the role of the government? Is there any mandatory training that the technicians need to pass in order to handle ammonia safely in Philippines? Can you please comment on that? Thank you.
Okay. Technicians here are trained not just by the local, but also by international training. And also, we follow the local codes, especially for the OSHA, Occupational Safety and Health Hazard here. So GAIA's initiative is to share and to align with the government and the local guides, as well as the client, that we follow the safety practice, best practice, to avoid any emergency during repairs or activities.
Okay, my question was about the role of government. Is there a mandatory training that is requested by the government, by the association, to handle ammonia in Philippines? Or is it an industry initiative?
Actually, it's more of an industry initiative, John.
Okay, excellent. Well, hopefully we will see more and more of the latest technologies and automatic controls and low charge ammonia configuration, whatever they are, that will further contribute to the higher efficiency and higher safety. So thank you very much again for sharing all the information today with our delegates. I would also like to invite you right after the event, in about 40 minutes, we will have an informal Zoom meeting. Everyone who likes to join from all our delegates, so please join us as well. The link is in the resources on the console. We will also share it here in the chat with all the speakers. So in about 7 minutes, we will have an informal get together as well. So thank you to all gentlemen from GAIA. And with that, I would like to invite our next speaker, Mr. Alan Wang from Carrier. He's the CO2 sales manager for industrial refrigeration sector. So Alan, please join us. Hello there. How are you doing today?
Good, good. Hey, how about you?
Excellent, very good. Now we have went fairly smoothly through the event, so we are looking forward to your presentation and your take on another solution that can be applied in industrial refrigeration, food cold chain sector, and that is CO2 transcritical. So please start your presentation.
Okay, thanks, Xiao. Yep. So hello, good afternoon, everybody. This is Alan from Carrier. It's my great pleasure to present the CO2 transcritical system application in cold chain and the food process market. Okay, we come to the second page, which is the HFC phase-out plan. So here, I would like to echo the importance of the environment-friendly refrigerant application or refrigeration business. So since we have been seeing the massive upcoming renewable of the refrigerant in our business, so this is very important for our application in this area. So next page, please. So this one shows why CO2 is being selected as a refrigerant. So basically, we have four the good candidate of the CO2 as a refrigerant. The first one is it's environment-friendly refrigerant. So the GWP equals to 1 and the OTP equals to 0. So which is has no impact to your environment. And the second one is most important is safety of the refrigerant. So actually for CO2, it's being classified as grade 1, A1, which is non-toxic and non-flammable refrigerant. So it's pretty safe for the residential and the commercial application, okay? So come to the third and the fourth one, which is the same as CO2 has a very high efficient and cost-effective compared to the other refrigerant like ammonia or the HFC for the R44A or 410A, which has the good heat transfer performance especially at the low ambient temperature. Low temperature application. So that is the most effective for CO2 as a natural refrigerant. Okay, next page, please. Carrier has been a global HVAC and R player in the market to CO2 tech. So actually, we have about 4 technology. We have the CO2 cascade system applied to introduce it to the market. This is the most common technology we are using so far. We are using the CO2 as low side of the refrigerant and use high side, we are using ammonia or HFC. This is targeted to the application or climate application for the system. coming to the next 2004 and 2014 and 2016, we introduced the pure CO2 transcritical system into a market. And we have the different iterations of the CO2 transcritical booster system, which has a limited application range. It's only focused on the mild and cold climate, which has a very lower ambient temperature in the domain, in the range. But coming to the 2014 and 2016, we introduced two very big or climate product into a market, which is the CO2 transcritical with ejectors. This can be applied to all the domains through the warm climate, the mild climate, and the cold climate. So this is our technology journey to the CO2 system. Okay. So next page, please. This one shows the CO2 solutions for the warm climate. So actually, we aim to introduce CO2 for all climate, and the warm climate always is being the barrier to the technology because of the high pressure of the CO2 of the ambient temperature. Okay, so we have the different scenario or technology to address this high ambient temperature lead to the high pressure of the system, including mechanical subcooling, the parallel compression, or the modulating vapor ejector, which is being patented by Carrier to leverage or to greaten the system performance. This is the CO2 solution for warm climate. Okay, next page, please. This one is most likely the CO2 product marketing segment for Carrier. Actually, so far, till to now, we have about 18,000 products sold in globally, and it's by the data we have. We have over 50% of the market sharing in the market. And within the data we collect, 75% are transcritical CO2 system requirement from the market. So this is a very significant kind of trend of the CO2 technology applied in the market. So transcritical is the next phase. Okay, next page, please. This one shows Carrier CO2 product portfolio. We have the different product to address the different application needs, from the store expansion to the industry application. So we have from the minimum cooling capacity of the 3 kilowatts to the biggest one so far is 1,500 kilowatts for the industry application. So this is a complete solution to cover the different customer needs and applications requirement. Okay, next page, please. So come to the biggest one, which is cover or align with our topic today. So industry application. So our biggest industrial CO2 product is a power cooler. This is the biggest one so far we have in the market. So actually we introduced the biggest 6 cylinders compressor, which is close to 100 cubic meters power for the swept volume for each compressor. And all the control logic, all the key component design, like the receiver in the system, is Carrier design based. So this is a product we introduced to the market, and it's very high efficient, which is I'm going to introduce for next page, please. This is the product range for the power cooler. So actually we have 4 versions of the product. For a single evaporating temperature for the media temperature, which is for the cold room. And we have the single evaporator for the lower temperature, which is the freezing room. It's close to minus 32. The lowest temperature is minus 40 or 45. And also we have the dual evaporating temperature for the media temperature and the lower temperature. The first version I'm not highlighting here is for the secondary cooling. So we have the chiller version for the air conditioning, which used to use a secondary heat exchanger for the air conditioning application. For the applications range, so here we have the heat pump, we have the logistics center, we have a spot venue, and we have the ice rink, snow arena, and the food processing also for the supermarket and hypermarket. This is application range for the power cooler. Next page, please. Being a high efficient product for CO2 transcritical product, so we have two major enablers to make sure this is a high efficient. The first one is carrier patent modulating vapor ejector. This is the one we used to increase the system performance by uplifting the compressor suction pressure. So we are using the high pressure gas from the gas cooler, in some words, is condenser, to uplift the suction gas for the consumer. In that scenario, the inlet suction pressure of the compressor can be uplifted about 3 to 6 bar, which is to reduce the compressor power input. So this is the very simple logic. And based on the experiment data we have from field and the test data, the energy efficient improvement for this modulating ejector combined with the semi-flooded evaporator, the energy efficiency can increase about 17%. Here I take Shanghai, for example. This is from China. But if we are using, consider about the Southeast Asia country, like a Philippines or the Singapore, Malaysia, the ambient temperature is much higher, then we can gain more heat efficiency improvement. If, for example, if the ambient temperature is 30 degree, then the total energy efficiency improvement can up to 20%. So that is much significant energy saving for a big industry application. Okay, so that's his first one, high efficient product enabler. Next page, please. The second one is the heat recovery. So CO2 system compared to the conventional refrigerant like ammonia or our HFC system, the heat recovery, the CO2 can provide a multiple temperature layer of the heat recovery from low temperature to the high temperature. And also the heat recovery amount is much more than the ammonia or the HFC system. So here we have did a very simple calculation. So we increased a little bit the power input to uplift the compressor discharge pressure to get more heat recovery from the system. Then the total heat recovery of the COP, consider the heat recovery, is up to 5. And also if we consider only about the cooling, the COP can be 2 or 2.2 to 2.3. Now we say heat recovery can up to 5. This is a very, very big improvement of if we consider a scenario of the both heating and cooling requirements simultaneously. Okay. So this is the second enabler of the power cooler product, which is the significant heat recovery provider. Okay. So next page, please. Next one is I'm going to go through the case study. So we have 4 cases to demonstrate the CO2 transcritical product application. The first one is the large distribution center in Finland. So this is a country-wide, country-sized logistics center. So the total refrigerant area is about 30,000 square meters, and the total height is 22. So this is very big, and it covers the cold area, the frozen area, and the blast freezing area within the 2 racks of the around 3,000 kilowatts for the cooling capacity. Next page, please. This is some of the technology we are using. So first one, this area is the ammonia is not is constrained to use is this area, and in the meanwhile we're using a big spring water tank as energy buffer to store the energy for the heating in the winter, and also the subcooling in the summertime. Okay, and also considering the heat recovery system, so we designed the heat network within the CO2 product, the heat recovery, so to gain the biggest benefit from the system. And also considering the system EER, below the 10 degree, actually the CO2 has much more significant benefit compared to the ammonia system. Okay, next page, please. So this one is the kind of some of the benefit we gain from, or the case study from Finland distribution center. So the electricity using from the system here is by the natural resource, the wind and the water. So the emission of the CO2 is negative. So compared to the ammonia or the HF system, the CO2 emission is much less or even a negative. And also for the energy cost, if we compare it to the conventional refrigerant system, the energy cost about 20% saving, within the similar size of logistics center, and also within the demand of the load shaving at peak usage. If we will count or done count for this side, the total energy cost reduction is about nearly 70%. So this is very attractive to the customer. And also, as a result, we get a very kind of the positive feedback from the customer, which is they highly recognize the system and recognize the solution. Okay. Next page, please. The second case is another logistics center in Spain. Here, we list here is to demonstrate the warm climate application for CO2 transcritical. So in this case is close to the South Europe in Spain, Valencia. The maximum ambient temperature in the summertime is close to 43 degrees. It's pretty hot. And while the system is running smoothly, so we can make sure the system is run safe and smoothly. And of course, we can gain some of the benefit for the modular ejector operation. Fancy the temperature is high, and we can gain more pressure left by the modulating vapor ejector. So this is the second case for the Spain. Next page, please. Next case is another case study for the food processing industry. This is one facility in China. So we are counting the comparisons between the ammonia system and the CO2 transcritical. This is pretty similar for the cooling capacity of the two units. And we count for about 1 month operation for the both system. You can see the chart here. In August, this is the most hot season in China. And these two facilities are running in sequence because they have different duty. And we count the operating time, hours, and we have the energy power to account for the total electricity consumption. So based on the timing, the data we collected from the field, the total energy saving for the CO2 system is about 8% saving than ammonia system. And please bear in mind, this system has no ejector. So if we have the ejector equipped in the CO2 system, then definitely we can get more the energy saving compared to ammonia system. As I just mentioned, the ejector can uplift to about 17% of the energy saving. So for this case, if we are using the ejector, then of course the energy saving for this system is much higher. We would imagine maybe a 15% or even 20%. So this is the case study for the food processing industry. This is third case. Next page, please. The first case is another case study, which is a little bit irrelevant for the industry code room. This is also for the CO2 transcritical application. This is for the China National Speed Scaling Over. So actually, this is our build for the Beijing 2022 Winter Olympic Game. So this is the ice rink for the speed over. So actually, the ice surface is around 12,000 square meters, which is the largest in Asia domain so far. And this have a 400-meter speed skating track, and also have the two ice rink about 1,800 square meters for the two ice rink. Also, this is the first CO2 transfer technology for direct cooling applied in Olympic Games. So we have some of the CO2 applied in the South Korea, Foshan, or the Sochi in Russia, but this is first transcritical CO2 technology application for the Olympic Games. And the total project size about 36 kilowatt for the cooling capacity, and we equipping about 6 CO2 rack, and for 600 per each for the cooling capacity, and the CO2 total charge is 43 tonnage for the system. Okay. Next page, please. This is a simulation of the system impact by unit of CO2. Actually, we simulated the annual energy consumption of the CO2 system compared with the HFC. So the CO2 system has about 28% of the energy saving by the whole year operation of the system. And it saves about 2 million kilowatts electricity for the whole year. If we count for the household consumption, it's about 6,000 urban household in Beijing for 1 month's consumption. So this is a little bit kind of significant of the energy saving. And also for the environment side, for the carbon emission, so we actually for this case, there's no, or the carbon emission is close to zero. And by the impact of the system, we have about, the carbon emission equals to about 4,000 vehicles emission per year for the carbon, and equals to plant 1.2 million trees for the environment. So for this case, it's both for the energy and also for the carbon emission. The benefit is very significant. Okay. Next page, please. This is a quick guidance of the heat recovery application for this case. As I just mentioned, the CO2 system has a very good heat recovery, cover the different temperature range and a very big amount of the heat capacity. So this is exactly the application of the heat recovery in this case. So we have the lower temperature range of the anti-frost heating for the ice rink, which is for the 15 degree. And for the middle temperature is about 30 degree for the ice pour melting to melted ice. For the high temperature range, the 85 degree for the water is for the hot water, and for the ice resurfacing and the dehumidification. So that's it for the high side of the application. So this is very big variety of the heat recovery application for CO2 system. Okay. So that is I know the time is very short, and this is a quick, the guidance of the CO2 transfer application for the cold chain and the food processing application. So long story short, CO2 is a good refrigerant, and it's deserved for us to explore in the future. Okay, that's my sharing.
Alan,
thanks.
Alan, thank you very much. Very informative presentation. We have time for a couple questions, so please stay with us. We have a question from the audience, and the question is as follows. What are the source and heat sink temperature levels for a heat pump from the example with COP of 4.73?
You mean the temperature of the application for the 4.3 for the heat COP?
Temperature of the heat, temperature of the source and heat sink.
So actually, we are kind of about 60 degree of the hot water. That is outlet. Okay, we are kind of about 40 inlet and a 60 outlet for the heat.
Okay, understood.
Okay,
thank you, Alan. You have talked about examples from Finland, from Spain, and from China when it comes to a distribution center, a warehouse, and food processing. Now, are you in discussion regarding projects to be deployed in Southeast Asia using this technology?
Actually, we have some of the potential requirement from South Asia. So actually, the customer is very interested about this technology, and we have some project running to deploy this technology in this domain.
Okay, understood. Now, what do you hear from your customers or from your colleagues on the ground? What are the challenges when it comes to introducing CO2 transcritical in the industrial refrigeration in food cold chain in Southeast Asia?
My understanding for the CO2 application for industry range or application, and I think it's the most challenge is to understand the customer requirement, because if we only count for the cooling requirement, then the CO2 is not, I would say, might not be competitive of comparing within the refrigerant, the HFC or the ammonia. But if we consider the simultaneously the heating and the cooling requirement, for example, if the cold chain had the food processing, or they have the big amount of the heating requirement, then the CO2 is a good alternative of the our solution. This is the first one, to understand the requirement. And the second one is, so far we know the cost of the CO2, right? And it's so far this is a new thing at some time, right? At some I would say that one. So it's from the Europe and to use South Asia, the cost can be a challenge to the customer, right? This is the second one. The third one is the technology application, because this is new and it's not widely used. So we need some time to explore, to capture the technology in the domain, like for the service, maintenance, installation, something like that one. Yeah.
Indeed. Yourself, you are based in China and you have a strong team in China. Can you maybe give us a short description of what was the story of CO2 transcritical in China? Because as we know, it has started some 3-4 years ago. And right now we are talking about some 10 systems in retail, and we talk about some maybe under 5 CO2 transcritical projects on industrial scale. Can you maybe tell us a little bit about how this journey started and about the current trends? Because this might be applicable to the region of Southeast Asia a few years down the line.
Yeah, sure. Yeah, my pleasure. So actually for the application in China, so we know China is the boosting market for all the technologies, and then typical for CO2, actually we started from different applications. From the retail, we started from the C-store, the convenience store for CO2. We have the CO2 CDU for the application, and then we have retail, which is supermarket and hypermarket. We have some case running, and come to bigger. We had food processing. We had the big sport venue, like the ice rink. That is I would say, from the domain, so we are applying the CO2 to the different applications, from the small one to the bigger one. And for the numbers of this application, so we have several players in the market. Okay, we have the several cases, as I just mentioned. We have the case for the C-store, we have the case for the hypermarket, and then we have the case for the food processing. So that is the number is, I would say, so far is it's not like the quite amount of compared to HFC or ammonia, but the number is increasing slide by slide. I would imagine in the next future years, as the guard KILIC kind of amendment phase out plan taking place, then this number will go up higher, and it goes up and up. Yeah.
Thank you very much. Just maybe two more questions. Should there be interest for your technologies and your expertise in Philippines or other parts of Southeast Asia? How is the best? How can the industry best reach out to you or your colleagues? Do you have offices in Southeast Asia? Are you ready to talk about these solutions in let's say places like Manila?
We have the sales office and we have an application team in Southeast Asia country. So we are based in Thailand and Malaysia. We have the carrier office in this and based in Singapore. So we have colleagues there. And for the CO2, I think definitely you can reach out to them first if you have the request from the customer. Then also for Asia, we have an CO2 application team, which is we have the training, the service, or the strong kind of technology for CO2. Definitely we will be a background, the backup of the team in Southeast Asia.
Excellent. Thank you, Alan, for sharing all the information and about sharing the case studies, which are always very good examples of how these technologies are deployed. We are aware of the CO2 transcritical systems being running for several years in places like Indonesia, also recently Malaysia, on both retail and industrial. So it will be very interesting to see how these technologies will continue to be introduced in new sectors and in increasingly more countries. So overall, we see a bigger competition between the natural refrigerant solutions, and the winner will be the end user. That's what I believe is the common goal for all the stakeholders. So Alan, thank you very much for joining us today and for your presentation.
Yeah, thank you. Yeah.
Thank you.
Yeah, thank you.
All right. So thank you. Bye-bye.
Yeah, thank you. Bye-bye.
So we are now ready to enter our conclusion. We have just a few minutes to go, and I would like to first of all say thank you to all our speakers and of course all our delegates. We had in the end more than 250 registrations, which is more than we had in our past events. So thank you for joining us today. So to summarize, today we have heard from several speakers, and we have really been able to discuss about different technologies based on both ammonia and CO2. We have talked about maintenance and safe use of ammonia, importance of training and different components, new technologies, including controls and IoT and use of artificial intelligence. And we have heard about a number of examples that have been deployed in Asia Pacific, as well as in Europe. So overall, the purpose of the Cold Chain Innovation Hub and the project is to bring the attention of the international industry to help share the best practice and really help increase the availability of the knowledge and expertise and access to the best that is out there in all sectors of the cold chain. So we believe it was a very interesting event with a lot of good content. We will be sharing the presentations already as soon as, I believe, tomorrow or latest Thursday. We will also be working on the recordings, but we will share the presentation as soon as Thursday this week. So thank you very much, everyone, for joining us today. We look forward to both the informal Zoom get-together for half an hour after the event, as well as we look forward to seeing some of you, or most of you, and many others during our virtual trade show next week, during the live webinar of the Cold Chain Innovation Hub. We will have presenters from DENR, from TESDA, from UNIDO, and we will also, for the first time, introduce a concept of the physical space of the Cold Chain Innovation Hub that we have been working on. So we hope to gather more stakeholders from the international community to really project what the Cold Chain Innovation project mission is about, and increasingly build this network of stakeholders. So thank you on behalf of my colleague as well, Devin and Gilda. We have hereby concluded the second technical training workshop focusing on advanced industrial technologies. Tuning in, and we will be starting a Zoom meeting in about 60 seconds from now. Thank you very much, and have a good day, all of you.